Hello everybody, this video is about understanding and calculating the equivalent resistance of a network of resistors. This is a simple concept, but sometimes it's easy to get confused about it. So let's take this with example. We have this network of resistor and first of all we have to understand that there is not for one network of resistor there is not only one equivalent resistance because it depends from where to where we pick the resistance. So I calculate here the resistance between A and B, A and C, A and D, or these four terminals of the network. Okay? And for doing so, I can just rewrite the network in some shade that it's maybe can be more easy to understand, to visualize the equivalent resistance. So, for example, for the resistance between A and B, I start from terminal A, then I find R1, then I split into two, R3 and R2. Then here I have my C terminal, but I don't care about it. Then I have my R4, and then R4 and 3, they combine back, and I have my B terminal and also the D terminal, which is actually the same. Anyway, this is what we have. So we can say that the resistance between A and B is equal to R1 plus what we have here. R1 plus this is equal to RAB. And what we have here is the parallel between R3 and the sum of R2 and R4. We don't care about this terminal because, they are just, that we are not interested in this because we are calculating the resistance between A and B. We can also visualize this with the current. So current with from A to B would follow this path. And here it splits into current and then come back. So this thing is basically the same thing that you have seen on this graph. So let's continue and see for other example. So for example, if I want to calculate the resistance between A and C, I will write down something similar but not the same than before. So I have my terminal A, I have again R1, then I split into two branches. In one branch I have R2, and then I have my terminal C. And then on the other side I have R3, also B, but I'm not interested in it. And then, which is also D, same contact. Basically, there is a cable between B and D. And then, and then I will have R4 and then C. As before, we can see this with currents, let's say currents. So from A to B, I have this path. From A to C, I have this path. Then I split into two. This one arrives to C. The other one make this path. Come back here and join it. So this vision is actually the same than in this drawing. From A to C, I have to follow this path. And with this path, I can obtain my equivalent resistance, which will be, in this case, R1 plus this block here. This block here is R2 in parallel with the sum of R3 and R4, which is what I state here. R1 plus R2 in parallel with R3 plus R4. Okay, so now we can calculate more resistance in this network. Delete the last drawing. For example, for obtaining all the combination, I also calculate RAD, but actually RAD is the same than RAB because B and D are just connected with the cable. So we have a equipotential value here, and basically the B terminal is the same than the D terminal. Okay, so actually R and D is equal to R and B. You can test this and calculate this with the drawing and with the current flow. Let's see how much is, what is the expression for RBC. So from this, from B to C. So from B to C, we have this current flow. Wait a second. We have from B to C, we have the terminal B cable, which is also the terminal D, but I don't care about this. And I split into R3 and R4. R4, I'm calculating between B and C, so R4, I already have my C terminal. R3 splits into two. I have R1 here and my terminal A. And then R2 here and then back to C. The same stuff with currents. B, okay, go this way, but also this way, and comes to C. Now current is flowing into R1 because it's an open circuit. The A terminal is just open. No current can flow here. I mean, I'm not going into this direction. I'm not going to A. So R1 actually doesn't contribute to my equivalent resistance. So this thing will be the parallel between R4 and the sum of R3 and R2. As I have here, RBC is the sum, the parallel between R4 and the sum of R2 and R3. I hope this explanation is clear. Anyway, so we continue with the other example. If you have questions, you can put in the comments. The resistance between B and D. Actually, this is 0 because B and D, they are connected with a cable. So if I have a current here, the current would just do something like this, direct. They doesn't find any resistance here, so it's direct from B to D. A cable, and so this resistance is actually 0 because B and D actually they are the same terminal. Okay, because on the same cable, on the same equipotential point. Finally, let's calculate the resistance between C and D. So C and D. I have the C. From C to D, I have this path. Okay, and also this path. I don't go into R1 because it's open. Current will not go here because if current go in this R1, there is no place where the current can go. It's open. So my resistance, equivalent resistance between C and D will be something like this. The C point, the C terminal, I split into R2 from one side, R4 for other side, and then I have my D here. And after R2, I have another split, which is R1 here with A terminal, and R3, which directly goes to B and D. So my resistance between C and D will be R4 in parallel with R2 plus R3. I don't consider this resistor because I have no current flow here. So basically, I have this result. RC is equal to the parallel between R4 and the sum of R2 and R3. So let's see other example with another network, and so we can better understand these concepts. I have here another network, and I show you some example of equivalent resistance. For example, with this network, with these 5 resistor and 1, 2, 3, 4 terminal that I consider, I mean, I can put other terminal in other places of the network, but I consider this for this example. So let's calculate RAB. RAB, I have my terminal A, from one side. Okay, so between A and B, I have actually R1, and I have already B here, R2, and it's here. And also I have on the other side, on this side, between A and B, I have all these resistors. So basically I have this thing here, R5, R4, and R3, and then B. I have C here, but I don't care about this. So it's R5, R4, I have D here also, I don't care, R4 and R3. So basically the result is the parallel between R1 and R2 in parallel with the sum of R5, R4 and R3. Okay, this parenthesis here actually is redundant because parallel, I mean, I can also avoid this parenthesis here. Anyway, you see this from this drawing. And this is between A and B. Let's see what is the resistance between A and C. So between A and C, I have A. Then I split into this thing, R1 and R2. Then I have R3, and I have my C point. I have B here, but I don't care. And on the side between A and C, I will have R5 and R4. D in the middle, but I don't care because the current flow in this direction. So in this case, I will have the parallel of R5 plus R4 in parallel with what? With all this block here, which is R3 plus the parallel of R1 and R2. So parallel of this R1 and 2 plus R3, and all this thing in parallel with this branch, R5 plus R4. Okay, so let's see the last one, and you can check if you want to test yourself the other combination. So RAD, between terminal A and D, what we have? A. So between A and D we have R5. R5, okay, in this branch, and the other branch is all these networks here. So I will have these two, R1, R2, then R3, and R4, and then D. So R1 in parallel with R2 plus R3 and R4. So the total will be here, I have the solution, R5 in parallel with all this thing. And this thing is R3 plus R4, R3 plus R4, because they are in series, plus the parallel of R1 and R2. Okay? I hope that this video was helpful and you are now, the concept about calculation and understanding of equivalent resistance is clearer. It's more clear for you. Thank you very much for your attention, and if you are interested in this subject, please follow and watch also all other my videos.